Today is the second half of genetic algorithms. Last time we talked about binary encoding, and that's where we took our design variables and turned them into a sequence of zeros and ones, kind of meant to mimic that genetic makeup of DNA of A, G, T, C. This time we're gonna look at real encoding. That's a bit more natural, perhaps, from our perspective, maybe less natural in the genetics motivation, but we'll see how it compares, some of the pros and cons. Before I do that, I'm going to do a little bit of an example just to show you kind of what this looks like. There we go. So this just happens to be in MATLAB, and only just because there's a GA that's already existing. So this is not one that I wrote, although I may show you one of those too later. This is just a commercial one. And we're running the Rosenbrock function here. So all these little black dots, those are the members of the population. You can see there was a bunch initially spread out. Over time, they're going to start to converge more towards each other. And now we're kind of in that valley. It's going to kind of stagnated the population. It was very similar. It's going to take a long time to kind of improve from there. So we can let this go for a minute, but you can see here, we can see the number of generations, the number of function calls, the best function, the average function, and I'll mention this one in a second. So when will this stop? Convergence criteria is a bit tricky for a genetic algorithm. We might look at the mean, but that's not really that useful. We don't necessarily care about how the average member of the population is doing because we're going to take the best anyway. But looking at the best is also tricky because the best will often stagnate. It won't change for a while. So that's what stall generations means here. It's showing how many generations in a row did the best not change. And so if you do use that as a criteria, you have to make sure that it doesn't change for quite a while. And in fact, most algorithms, it won't change too often because you use something called elitism. Elitism means that we take the best member of the population and we set them aside during each generation. So they don't, or set them aside for the selection process, I should say. So they don't get killed off by, survival of the fittest. That way we're guaranteed that our population never gets worse. It might not get better. The best might stay the same, but it won't get worse. Okay, so here the criteria is a maximum number of generations. So that points to actually what's a typical criteria. It's hard to perform some rigorous convergence because we don't have a gradient, and convergence can really slow down often. And so typically what's used, you just give it a budget, like this is how many generations I'm going to run. So here's the answer we got. The true answer, of course, is 1, 1, and this answer is 0. This isn't obviously a really high tolerance, but it's it's decent. We know we're going to get different answers. We run it so let's just try again. We might get lucky and do better, or we might do worse. Seems to be congregating further away. So this might take a while. We'll see. So another way, which is kind of the same thing, is that we'll often watch this, and you can see this has a stop button. So many methods will allow us to intervene and say, okay, let's just end it. We'll kind of monitor progress and say this is good enough. It's kind of stagnating, or I've gotten enough improvement, and we could stop it and see our solution. Yeah, we might try this one last time, see if we do better. This time looks like we got lucky, right? One of the initial points was really close to the optimum. So this is going to converge pretty well. We're going to cluster around it pretty quickly. Well, they're backing up a bit. And we'll stop it here. Okay, so that's just kind of a general feel for how this looks. Let me switch my screens. We'll dive into the methods a little bit. Just a second. Okay. All right, so like I said, today we're going to be looking at real encoding, meaning we're not using the binary version. So let's talk about some of the pros and cons first between, let's say, a binary and a real encoding. So for real, let's say there's some advantages and some disadvantages. Okay, and my shorthand. You might take a minute and think to yourself, what might some of these be? Well, one advantage is that we have now arbitrary precision, not really arbitrary, that's maybe not a good way to say. We have machine up to machine precision. Right, whereas before with binary, remember the number of bits we chose was generally not going to be a huge number. And so we had kind of these discrete steps that we could take. So we couldn't really get a very precise answer. But now that we're using real variables, we can use up to machine precision. Another advantage you might have thought of is that, we avoid that whole encoding and decoding stuff. Remember we talked about how do we convert this number, say diameter is 8, or a more interesting number like 8.4. How do we convert that into this 0 and 1 representation? And then how do we take the 0 and 1 and bring it back? Because we need to bring it back so we can evaluate our actual analysis function. Now we avoid all that, right? Just pass in 8.4. Let's just use it directly. One advantage that's maybe not so apparent is that we avoid what's called the Hamming cliff. Oh boy, let me rewrite that. Hamming cliff. Okay, so what's the Hamming cliff? Well, imagine I just had 4 bits. So, and we're just using spacing of 1, just carve a simple generic binary. This number here, that's 7. And this would be 8, right? 2 to the 3rd plus 0, this is 8. So in other words, to get from 7 to 8, which would be the next number in the sequence, just I want to increase a little bit, because I got spacing of 1, I'd have to flip every single bit, right? So that happens every time I fill this up with ones and I want to go to the next one. So there's kind of these periodic cliffs here, right? Where changing from 1 to 2 is easy. I just flip 1 bit, but then going from 2 to 3 requires, a bigger change. It's maybe not the best example because we're only running with 2, but say I wanted to go from 6 to 7, I change 1 thing. Let's go to 7 to 8, I got to change 4 bits, and that's less likely, much less likely, right? Especially as I have more bits, just for that to naturally happen. So it makes it a little bit harder, the design space a little weirder. So another thing that's maybe not apparent is that this actually ends up, this real version is usually more efficient. Now this is typically the default when you use a GA. And I should say, I showed you this MATLAB one, a popular one that you might find in many languages. It's called NSGA2. There are lots of versions, but this is one that you might also look at. You can find that in many different programming languages, some implementation of that. But the default in most of these genetic algorithms is going to be to use real encoding. Really, the only reason to use binary encoding, I would say, is if you have discrete variables, right? And so, of course, that's our disadvantage here with real, is that we can't use discrete variables. And this isn't a disadvantage, I guess, conceptually. It's not really a disadvantage practically, though, is that the crossover, mutation, they're less natural. With the binary version, and that's kind of where things started, they more mimic closely the genetics. So there's kind of a natural interpretation. For real encoding, it's less obvious, like how should we perform that step, because this just doesn't really have the same kind of analog. But that's less of a problem practically, because even though it may be less natural, the methods we use, this ends up being more efficient anyway. So again, sort of to recap there, this is what's used now most of the time as a real encoding, unless you really need discrete variables. Okay, so let's just go through each of the main steps: the initial population, then selection, crossover, and mutation. The initial population, typically, again, we would use a Latin hypercube sampling. That's really kind of thing to use, but let's say you didn't want to do that, you want to do something really basic, you could just do a random sample. So you're going to provide bounds. Let's say this is the lower bound. Well, let's use a notation we have been using. It's a lower bound in X, and right like this, upper bound, lower bound. Okay, so you provide upper and lower bounds for each variable, and then ours is a random number. We're going to generate a bunch of random numbers. All this does is we're, randomly choosing numbers that fall within the bounds that you provide for each variable. It's not as effective in Latin hypercube sampling, but that's easy to do. And this also, again, highlights this point I was trying to make last time, is that you have to be more careful about the selection of your bounds, because if you make these too big, your population is going to be really spread out. If you can imagine that Rosenbrock problem we just saw, imagine you're trying to search that really large space. It's going to be way harder to kind of find this sort of narrow valley you're looking for. Again, you don't want to artificially constrain it where it's so small that, you're just hitting the boundaries to find the good solutions. But, you want to try to keep this tighter than you might normally with the gradient-based method. All right, selection, this is easy because nothing changed. The methods we talked about, like tournament selection, roulette wheel, all of those just are looking at the function value, so they don't actually depend on the encoding, right? It doesn't matter if we're using real or binary. All we're comparing at the end is the fitness, right? So nothing changed. So that was simple. Crossover and mutation are the ones that are going to have to change. So remember what we did before. We had this string of bits, 0, 0, 1, 1, 0, 1, 0, whatever, and then we had another one, 1, 0, 1, 0, 1, 1, 1, or whatever, and we randomly chose the spot, and we said, let's take this first half of this one and combine it with that one, and then take this and combine it with that one. Right? That's not really going to that's not necessarily going to work directly with a real number. So we'll look at two variants. Actually, I'll first show you the one that's similar to that, but this is maybe less popular, and it is to do kind of the same idea. So imagine I've got two parents, parent one, parent two, right? And parent one has design variables. We'll make parent one, we'll write it this way. Let's say it's got x1, x2, x3, x4, x5, right? These are all the design variables, and these are real encoding, right? So this number here, say 19.2, whatever, it's some real number, right? Parent two, I'm going to use a different color. Parent two has its own set of design variables, x1, x2, x3, x4, x5. So we could use the same approach. We randomly select some place. So, run a random number generator. We say, let's divide things here. And so then our two children become, take a top of one, bottom of the other, x1, and then x2 with the blues, right? The bottom one, x4, x5. And then the converse, right? Child two, it's going to be x1, and then the top part, x2, ... right? That is fine. That kind of just mimics the same idea that we had. It's called a single crossover. This is not usually as effective because it doesn't generate as much diversity. When we had the zeros and ones, like splitting it somewhere, it could be splitting in the middle of a design variable and we can recombine them. It tends to create more diversity. This one doesn't, right? Because most of your design variables are going to stay the same, and then you just kind of swapped some set of them. So it actually relies more on mutation to kind of fulfill that role of diversity, which is not usually the best place to do that because it's a lot more random. Like here, we're actually trying to use parents that have survived many generations and are getting fitter. So anyway, this is maybe less popular, but it can be used. It's analogous to what we've done. So what's often used instead, or here's one variant, there's lots of variants, right? But here's just one, it's called linear crossover. It's maybe more accurately called blending, but we'll just use the name that's based off binary case crossover. And what it means is we'll still have two parents and we'll make one child, and these weights, could be changed, but let's say we make one child that's the average of the two parents. Okay, so here's parent one, here's parent two, you multiply them by 0.5 and add them. And so that, in other words, the child takes the average of the characteristics of the two parents. So here's that pictorially, here's parent one and parent two. This first child becomes kind of an average. And again, those weights, could be adjusted or whatever. And then usually we do something else, something different with child 2. And here's one variation is that we could say, let's take the weights and bias them towards parent 2. So where parent 2 is the fitter one. So in this case, the objective for parent 2 would be less than parent 1. So we take the better parent and we have the child adopt more of the characteristics of that parent. So this would be pictorially be like this. Here's 1 and 2 is fitter. So we pick a design that takes more of, if you took kind of a line through these characteristics, moved more towards the parent 2 direction. And like I said last time, sometimes we don't take the children directly, we take the best of now these 4, and those 2 best become the new population. But again, there are many variants. Okay, so this is one that's maybe, like I said, doesn't really pattern genetics per se. It's maybe less natural in the analogy, but one thing to keep in mind with these bio-inspired algorithms is at the end of the day, we're not trying to do the, we're trying to take inspiration, but we want to create an algorithm that's going to be effective. And in practice, these real varied ones, real encoded ones are more effective. So even if it doesn't mimic exactly, or even at all, the actual biological process, that's okay, right? Because that's not really the goal per se. We want to take some things that are going to help to inspire an idea, but if we can find something that's more effective for this algorithm for our particular purpose, which is not really the same as genetics, then that's great. Okay, so mutation again, also a little bit less natural, because remember before, it's kind of maybe mimicking what you might see in a genetic where a single gene might flip or something, or a few. We don't have that. We can't just like take a real number and flip it somehow. So what we do instead is we randomly perturb some of these values. So for example, we might go through each design variable xi, and with some probability, we're not going to randomly perturb everything, but with some probability, we might perturb it by some amount. So in other words, I'd visit each design variable and I'd generate a random number, and let's say it passed my threshold of 1 or 2% or whatever. If it was above that, I'd say, okay, skip it, go to the next one. And I get to design variable 5 and it hits my threshold. I say, okay, I'm going to perturb that. Then here I could generate a number between 0 and 1. So what this is doing is say, here's my, here's X, let's just say it was 1D, and this is delta. Delta is this size, right? It's randomly choosing a number that's in this interval. Because if I chose a random number of 1, it's going to give me, this is going to be 0.5, so it's going to move me plus 0.5. If this was 0, it's minus 0.5. So I have to choose beforehand like some sort of spacing or scale, if you will, of perturbation, and then I randomly sort of perturb these variables by some amount. Okay, so again, just to illustrate that, let's just say I had 3 design variables, 2.1, 4.6, 9.1, and I go through, I generate a random number, it's too high, oh, this one meets my threshold. It was, really small, 0.01, it was less than my 2% threshold. So I'm going to perturb that. And so I might add some small number. I pull up my random number generator and I add, let's say my width here was 0.1 and I generate a random number of 0.8. So 0.1 times 0.3 gives me 0.03. And so I add this small number. Okay, so I perturbed it by some small amount. And obviously this is going to be sensitive to how I choose that width. If I choose it really big, then my perturbations are going to wildly swing my variables around. If I choose it too small, then mutation is going to have no real effect. So I have to think about kind of the problem, what makes sense as a scale. Another variation that's used is to, instead of use this uniform variation, we could use a normal distribution. So we could sample from a normal distribution, a Gaussian distribution with mean 0 and some standard deviation that we choose. So this would be kind of like the same one before. Here's xi, but we'd have like a bell curve on top of that. And so we'd randomly pick some number from there. And so, we have some finite probability that we could pick something way over here, but it's most likely going to stay within, say, about 3 sigma plus or minus. That's just another approach that could be used. Again, less natural, right? I mean, our genes don't have some continuum where they can randomly well, maybe there's something like that, but in general, they're just going to flip between these different options. So the other one is maybe more natural, but this one is still is really effective. Okay, so that's really it. All the steps are really the same, but we just had to change mostly just these last two, right? Mutation and crossover. But this ends up being effective and more natural, right? Because then we can inspect the design variables more quickly. We don't have to worry about encoding and decoding. It's going to be more efficient, but we still do have that other option. It's not as efficient, but if we need it for discrete variables, we can use it. We will, as I said, talk about other methods for discrete variables, many of which are going to be usually much more efficient, but it's still nice to have that option. It can be a good option at times. All right, so next time we'll talk about a different algorithm called the particle swarm method.